By the early 1950s, chromatography had been used to separate amino acids. The next big challenge was to use it to purify proteins. The main problems were that most proteins were too large to partition into typical resins, and they would often irreversibly adsorb onto common organic resins, making recovery impossible. Many prominent scientists of the day actually thought that chromatography would never be useful for separating proteins. The solution was to use different resins. These new resins would need to be porous, yet strong enough so they didn't collapse during operation, and hydrophilic so that proteins would not irreversibly adsorb to them. One of the early resins that met these criteria was cross-linked dextran. Its development actually led to a new type of chromatography, where molecules were separated based on size rather than relative affinity to the resin. Today, this technique is known as gel permeation chromatography, gel filtration, or size exclusion chromatography. This cross-linked dextran was developed in 1959 by Jerker Porath of Uppsala University in Sweden and Per Floden at Pharmacia, also in Uppsala. But the story of its development actually begins in 1941. At the time, the Swedish sugar manufacturers approached the laboratory of Arne Tiselius at Uppsala University with a problem. Some of their beet extracts were contaminated with an unidentified slimy substance. Tiselius' student Bjorn Engelmann eventually identified this substance as the polysaccharide dextran from the bacteria Leuconostoc mesenterides. During Engelmann's study of dextran, he also cross-linked the material, forming a gel. As this gel was not immediately useful to Pharmacia, which initially commercialized the dextran as a plasma expander, it ended up being stored on a shelf for several years. Eventually, the lump of dextran came to the attention of Per Floden. At the time, Floden was collaborating with Jerker Porath to develop new packing materials for electrophoresis columns. He resynthesized the cross-linked dextran and shared it with Porath for his electrophoresis experiments. In one of the first experiments, a visiting researcher in charge of the experiment actually forgot to turn on the electrophoresis current. But when they eluted the column, they surprisingly saw that different sized molecules moved at different rates through the column. Porath and Floden built upon these initial serendipitous observations, and in 1959 the first commercial gel filtration resin, known as Cefidex for separation Pharmacia dextran, came to market. Cefidex is still sold today. You can understand gel filtration by imagining a group of people exploring a cave. Everyone starts together at the mouth of the cave. Some of the rooms and passages are smaller, so only shorter people can explore them, while the taller people skip the small rooms and continue moving through the cave. The smaller branches might have other, even smaller branches that the shortest people will continue to explore. The others will turn around and head back to the main part of the cave. This process would happen at each branch in the cave, so the tallest people will emerge from the cave first and the shortest people last. Gel filtration works the same way, except the cave branches are pores within the chromatography resin. Large molecules pass completely through the column and are not retained, while small molecules, which can partition into the pores of the resin, elute at a later time. The goal of any chromatographic process is to separate two or more compounds. We need to return to the definition of peak resolution to understand the ability of our column to separate two components. You can see that the resolution is dependent on the distance between peaks on the chromatogram, as well as the width of those peaks. Therefore, to maximize the resolution, we need to increase the peak-to-peak distance or narrow the peaks. Let's start by looking at peak-to-peak distance. For gel filtration, the retention volume for a molecule on a gel filtration resin is given by this equation. In this case, V sub I is the intraparticle pore volume, V naught is the void volume, and K sub D is the partition coefficient of the molecule and is related to its molecular weight. Here, K sub D is analogous to the height of the cave branches, or how tall a spelunker would need to be to fit down a branch. And V sub I is analogous to the length of the cave branches, or how far a spelunker would need to travel to explore the branch. Given this, the distance between two peaks is just this equation. Therefore, choosing a gel filtration material with a maximum difference between K sub D2 and K sub D1 and a high pore volume V sub I will give the maximum resolution. Peak widths are a function of column efficiency. A number of factors play a role in the broadening of a chromatographic peak, including diffusion along the column, diffusion due to geometric effects within the column, and incomplete mass transfer during operation. Increasing the column efficiency by choosing an optimal flow rate and using smaller particle diameters of the chromatographic resin will also increase the resolution. Choosing a gel filtration resin impacts our ability to separate our product from other differently sized protein impurities, such as high molecular weight aggregates or host cell proteins. In the next segment, we will continue to learn about chromatography methods and how they are used for protein separation. And to think, all of this started with some slime on beets. So the next time you eat some pickled beets, remember their role in purifying biologic medicines.